scene where they were walking through the basement. Hey.
Hello.
All right, hey, Lassie. That's Nick. Lassie, goodbye.
Oh, hi. Great to meet you.
Well,
Hi. Hi. Nice to meet you.
Well, I was running the AV show here, hopefully.
Yeah.
All right, so what do we got?
I'm third on the bench. So
Third on the bench, yeah.
yeah, so I tested the laptops this morning, so it should be fine. Got the speaker mic on here, and lavaliers is having an issue with it.
What's going on with Lovely?
Just don't want to connect it back there and don't want to fiddle with anything.
Really? Can we?
Yeah.
I have HDMI. Can I
Yeah,
just go
let's just
straight?
pull that out, yeah.
Like you can keep that, like,
Okay,
and I can just go direct.
cool.
HDMI.
Should probably also done downstairs.
What? No.
Why?
That one is not ready yet.
Oh, really?
Yeah.
So can you get in here? Because I thought
Yes.
the microphone thing was supposed to be pretty straightforward.
Yeah, I don't know why they changed, why they said this is what they did.
We can't let Tom take the picture. Yeah.
Yeah, yesterday. Throwing two buttons.
If you sit like here, you can probably still play. I haven't gone to like a talk. I like never go to talks. But I kind of wish I did because that's like that's because we're not going to
Those are the mics in the seat.
Like I'm kind of realizing there's a lot of stuff I'm taking for
There are
granted
6 or
that I'm taking advantage of, and I want to like start doing stuff like this.
I made sure that they were turned on.
That's true. It's like, we won't have that kind of academic focus that a lot of times we do. And like they'll have CS ones, but I don't know. I feel like I should go to like philosophy talks and stuff. Oh, I see what you're saying. So you're gonna have all these people. I'm like, they're gonna give me bananas coffee. Yeah, this
I want to make sure that the laptop.
Yeah, exactly. Some things are getting done, which is nice and weird.
Quick question on timing.
like it's
Yeah,
I noticed.
I don't know. I guess that's just kind of up in the air.
Yeah, no, probably.
That's what I thought. Yeah, that's what I assumed. I just asked.
It might be he has got the confirmation.
How off the rails is she like this?
Why are you telling me? I hope someone doesn't have video. And they're also,
We've got like this high-end AV setup, which means no one knows how to use it. High-end, for entertainment,
You're
we
good at something.
show Sanjay's,
TV show.
that was awesome.
I love the attention. It was great.
like here, like,
That was great, so,
Facebook, Google.
Sanjay was on local TV.
Yeah, exactly.
And I love the question about, you use this word server several times. Could you explain what that is? I was like, wow. If it was me, I would have like shredded the guy. You handled it very well.
Could have had a podium about computer literacy up there.
All right, so we'll, no. Oh, yeah, and then this is on too. Yeah, no, we actually, believe it or not, that, those two big green things.
That square.
Yeah, that's for the recording. This is for the room, but this is. All right, we'll work on it. Okay.
That was mine.
Oh, no, this chair's okay.
I need to sit somewhere I can get out because I have to run the class.
Like, how are you getting there? I mean, do you have, so the question is, do you have, like, China? Huh? Heather, okay, so. Yeah. All right.
We're trying to make sure we have
All the math labs, these guys, and then Buffalo. I don't know. My friend described it so.
Better view.
We're going to talk about that.
It's steaming.
it's like BLDB first time. That's there.
It would have been much worse.
Hi, it's all done. Well, I would think now was the last chance, so, you know, they got about a month. It's just good to see all these places, so.
When you're ready.
Better get something out for the next month. You got,
Oh, interim thing. You might want to turn off your Wi-Fi. It's embarrassing. Oh, well, that room's weird sometimes. All right, great. So why don't we get started? So thanks to everyone for braving the cold. That you get extra points for doing that. So it's my pleasure to introduce today's speaker. We have Nick Feamster, who's a professor in computer science at Princeton University. He's also deputy director of the Princeton University Center for Information Technology Policy, which he also was the director of for 2 years. Nick is well known as a researcher in networking and related fields. He's won a gazillion awards. He's an ACM Fellow. He won the Presidential Early Career Award, Technology Review 35.
We get started.
Sloan Award, Test of Time, Usenet's Test of Time Award, it goes on. But I would instead rather let Nick do the talking, so I'm going to turn it over to Nick.
Thank you for joining me today. It's a pleasure to be here. I told the barber that I was coming to Chicago and they gave me this. It usually looked like that. But if you saw me this morning, I did manage to get out for a run. I looked like that. So two extremes, I suppose. This picture, I don't know if you recognize it. This is from 1969. This is basically the landing of the Eagle. Many people know 1969 is the year that we landed on the moon. Other people may or may not remember this event from 1969. Also, a few months later, this was one of the first nodes on the internet, called Interface Message Processor. When we landed on the moon, there's some quotable quotes. The Eagle has landed, one giant step, one small step for mankind. When the internet sent its first packet, the first words were low. Login didn't quite fully make it across the internet. A couple months later, it was fixed. But since then, I think we've made quite a lot of progress. This was arguably our last moonshot, right? And when I first started learning about internet architecture in school about 15 years ago or so, we talked about basically the design of that early internet, the interface message processor, the early nodes in the internet, and we studied this paper, The Design Philosophy of DARPA Internet Protocols, which articulates a lot of goals of the early internet. And a lot of you who've studied the internet will basically see these kind of properties listed in your textbooks, right? Survivability, reliability, etc. And it's interesting, the paper basically talks about, the fundamental goal of the early internet was basically just to connect heterogeneous networks, hence the name, internet, network of networks. We've pretty much succeeded, I think, at doing that. But since then, the internet no longer looks like that cute little picture, right? This is even dated. This is pretty, that's what it looked like about 5 or 10 years ago. It's also getting faster. There are more and more things connected to the internet. It used to be things like that machine I showed you on the previous slide. Now it's like anything you buy from Best Buy basically has an internet connection as well. We'll talk a little bit about that later in the talk. That brings me to basically what I see as sort of the future agenda, basically, of what the next set of challenges are for this modern internet. And I'm going to talk about all three. I'm going to talk about some work that we've done in each of these areas, as well as where I see this going in terms of an arc. First is sort of make it usable, and this is a foremost concern. There are many aspects of usability. I'm going to talk about a specific low-level aspect of usability that mostly relates to performance. And the second aspect is can we make it more trustworthy? And here, this aspect, the one aspect that I'm going to focus on here is how do we protect users from unwanted messages? In the early days, that really meant things like email spam. I'm going to talk a little bit about that. These days, it means, in the trade, we call it disinformation. You probably have heard it maybe as fake news. I'm not going to use that term in this talk, but beyond just what I just said, but we'll talk about disinformation. As it turns out, that topic bears a lot of similarities to email spam, both in terms of like how those campaigns are launched, which means actually there's some similarities in how we can detect them. Finally, I'm going to talk about privacy. Privacy, of course, is hard to define. We could spend the whole hour trying to define it and we wouldn't get anywhere. This problem is obviously not 100% technical. It crosses over into policy, law, economics, and many other disciplines. But in this talk, I'm going to focus on how various technical interventions can help us, move the needle in this area. Yes?
Just a quick definitional thing. When you say internet, are you referring only to sort of a network kind of layer, or are you including all the applications?
I'm going to talk about applications as well. Absolutely. Yeah. A lot of my work is up the stack. So I'm just going to motivate each of these a little bit to say a little bit what I'm talking about, and then we'll jump into each in detail. So usability, we're going to start talking with things about speed tests. You may have seen this case. This is something that I was intimately familiar with, as a resident in the New York area, and also sort of participated in advising in this particular case, because a lot of the basis for this charter basically refunding a lot of its customers for not delivering on its advertising was rooted in how do you measure internet speed. Okay, well that sounds like pretty easy, and conceptually it's actually pretty simple. It's like, well, I've got a bunch of bits, they need to move from A to B, and let's figure out how much time it takes for those bits to move from A to B. So conceptually, super simple. What could go wrong? Well, actually, it turns out that that's a really hard question, and I'm going to spend a good chunk of the first part of the talk talking about it. Let me give you a flavor for it. We've probably, a lot of you seen speed tests, speedtest.net, for example, maybe even run this tool. And this is something that I basically show on the first day of my networking course. I have students run this and basically just report back. Tell me what you get. What number does this thing spit out? And here's an example from last term. You basically get everything from 2 to 83 sitting in the classroom. And basically have a fairly long discussion about, well, why is that? Like, hey, the network is something you can measure, right? Why are we getting all these variable numbers? And we'll talk about that, but the short story is that this, even a really simple question of like how fast is my network, is actually pretty hard. And it's getting harder, and I'll talk about why. One of the reasons it's getting harder, and this is sort of where I think things start to get really interesting, is not only is the network getting faster, which introduces its own set of technical challenges, but users don't really care about, hey, I bought a gigabit per second from my ISP, let me click speed test and get a really big number. They care about, can I stream Netflix or YouTube? This is an interesting graphic, I think, because, hey, we've probably experienced the Netflix rebuffer phenomenon. This is interesting. The Verizon network is crowded right now. Well, how do they know? Turns out they don't. This is just basically finger pointing. But this question of like, where is the problem? Like, why is it that my video isn't actually playing back in the way that I want it to? Turns out to be a really interesting challenge, both technically, with a lot of implications for everything from network design to policy. Trustworthiness, as I mentioned, we're going to talk a little bit about spam. You don't see email spam very much anymore. That's good. For the most part, that email spam problem is solved in a sense. We spent a long time working on that. In some sense, that means we've done a good job, like designing our machine learning, to basically filter out the junk. But the problem has basically moved elsewhere. These are some examples of sites. London Web News is one, Got News is another. These are popping up like every day on Twitter and Reddit and so forth. And I'll show you some more examples later in the talk. But we're currently using some of the same techniques that we use to detect email spam to detect these kinds of sites as well. Finally, privacy. I probably don't even need to motivate this, right? But it is worth. This is from the Facebook hearings just a few months ago, which you may remember. It's worth pointing out, however, that this is not a new problem. Facebook actually was under a consent decree from the Federal Trade Commission to behave back in 2011, and as you can see, not much has changed. In fact, it's basically getting worse. Not going to spend any time on all these because we could, again, spend the whole hour on it. But I want to point out that obviously things are moving towards smartphones, right? Location privacy, etc. Also, I couldn't resist basically just putting up a couple of headlines from yesterday, right? You think VPNs are the solution, right? Well, it turns out no. Facebook has their own VPN. You can imagine what they're doing with that. Okay, where does my work come in? Well, if you think phones are bad, the smart home is coming, and I'm going to basically talk a little bit about all the work that we're doing to look at basically how these risks translate into the smart home. And what we can do to sort of mitigate those types of risks. These are pictures, by the way, from our IoT smart home of the future, whose paint is peeling. It doesn't have a great railing, but inside it's got a lot of cool stuff like internet-connected fridge, smart TV, and various other appliances that we're looking at. So those are the three topics that I'm going to focus on. Let me start with the usability one, and we're going to start with some of the work that we've done on speed tests. This basically dates back almost like 10 years. And then I'm going to end this part of the talk talking a little bit about our current challenges looking at quality of experience. As I mentioned, speed tests, these things are pretty common. Everyone, pretty much runs these. Even your ISP asks you to run them, but they're imperfect. I kept this one in here because this is quaint, right? Like, this is like when we started. 2 was fast. What do these numbers even mean? What am I measuring? ISP performance? Am I measuring my wireless? Am I measuring applications? It turns out, like back when we started, you were pretty sure that when you were measuring 2, you were measuring your ISP because it was the slowest thing on the end-to-end path. And that's actually just, it's no longer the case. Here's another picture of exactly the same experiment I ran from a few years ago. So way back when, we basically got the idea to instead of what would happen if instead of like running, from a laptop or a phone or some other thing that, you can't really, control in the user's house, what if we just like put that software on the home router? And the question is, what should that software be? And I'm going to come to that. But this was sort of the first kind of insight, was like, this home network thing is way too hard. Let's just like cut that out of the equation and start measuring right from the point where the ISP enters the house, okay? This has a lot of benefits in some ways, right? You cut out a lot of the stuff that, can mess up this particular measurement. It's always on, meaning you can basically continue to measure. Another thing with speed testing, right, is people generally use it when they've got a problem, right? So you have this weird sample. We were interested in getting more continuous measurements. Now the con, which we sort of turned out to be a lot harder than we expected, of course in hindsight you're like, yeah, obviously, is like you've basically got to deploy this stuff, which means you have to get into users' homes, and that turns out to be an interesting mess, which I'll talk about in a couple of minutes, but there's some systems challenges there. This is a picture from my own house. You can see it's pretty up and down over the last year. You'll notice this says multi-threaded TCP. There's another thing I'll talk about too, which is like, well, we can measure bits from A to B, but like what protocols are you going to use and how many connections are you going to use and all this stuff. And this was basically the root of a lot of the technical research here. Like I said, basically, measuring from the router gives you that hub viewpoint. You can isolate these interfering factors, like what's going on with the user's home wireless network. Are they running other stuff in the house? Well, if we're at the router, we can see that. We can test at a different time. We can subtract. There are a whole bunch of techniques that we can test there. We can also we can run our own measurements. We can also listen to the traffic that basically they're sending and try to make inference about that. And that brings me to some of our current work, which I'm going to wrap up this section of the talk with in a little bit. And as I mentioned, it's always on. We managed to get this into about 400 homes in 20 different countries. And we obviously published a few papers using this, which obviously is good. That's what we wanted to do. But other researchers, both in Europe as well as in various developing countries in Africa, have also made use of both the data that we've been able to gather as well as our deployment. Well, it turns out deployment's pretty hard, right? You put yourself like as the home router, you suddenly everyone's pointing their finger at their ISP, and like when you become the home router, everyone starts pointing their finger at you, like, boy, my connection's horrible. It must be you because it was fine yesterday. So a lot of times it was us, and we had to work some things out there. But even when you're not, you basically become tech support. This is a big distributed system, right? So a lot of sort of classical challenges there. There's also another one too, which is like, how do you basically provide incentives for people to like leave this thing in their house or put it there in the first place? And that's basically, I've shown you a couple pictures of the dashboard, right? If you give something, if you give the users a way to basically figure out what's going on in their own network, some people turn out to be interested in that. Let me talk a few minutes about some of the technical challenges and insights here. One of the big ones, as I mentioned, was this: how do you measure performance in the first place? And I love these kinds of questions because it's so simple. It's like, well, what's the network throughput? Well, we look at the textbook will tell you, right? It's like bits per second. Well, turns out there's like, as many different ways to measure throughput as there are people in this room. And we basically did a bunch of work looking at like, well, what happens when you use a single thread? And what happens when you open up 10 parallel connections? Or how many do you really need to basically saturate the link in a way that basically doesn't interfere with the connection that the user's trying to use, because you've got this interesting trade-off between trying to max out the pipe that's there and not basically creating so much disruption that people are like, hey, every 2 hours my network is melting down. Okay, so this is a careful trade-off. It turns out the right answer is somewhere between 3 and 4, or at least it was at the time, with hundreds of megabits per second, gigabits per second going into the home. That answer is changing. But that turned out to be an interesting aspect of the study. Another thing was basically we found a new metric, which turned out to have a lot of implications for the design of both internet architecture and protocols. It's called latency under load, right? So we understand the concept of latency, right? It's like how long does something take to get from A to B in time? Well, latency under load means like what happens when I load the network? Like I do an upload, right? What does my latency change? Well, in a well-performing network, it hopefully shouldn't. But like if you have buffers in the middle of the network and your senders aren't backing off, right? Those buffers are filling up, and your packets, your data is basically getting in line behind everything else it's trying to send, and nobody's slowing down because no one's getting the feedback to slow down. This concept basically, and this metric that we came up with, led to basically a lot of studies of a phenomenon called buffer bloat. And there was a lot of work, both in terms of router design as well as new transport protocols in the Internet Engineering Task Force and elsewhere to try to mitigate this kind of effect. What you may have seen this, by the way, yourselves, like if you're old enough to basically have been doing photo uploads and other things in the early 2010s, like, oh, I upload to Flickr or whatever, and suddenly I can't like browse the web. What's going on? Well, basically your massive upload has created latency in the network, and nothing else is basically working. Fortunately, we're seeing less of this, but these buffers were in everything from like your home router to the routers in the middle of the internet. So internet had to basically change to mitigate that. We published a paper on this, and also this particular metric is still used in the Federal Communications Commission annual report on the measuring broadband in America. Okay, problem solved, right? 2011. Well, sort of, right? So here's 2011, like and this is from the NCTA, right? So these are basically top cable internet speeds in the United States. There was nothing faster than 100, right? 2, 3, 10. That was pretty fast. Okay, now gigabit per second. Like obviously there are a lot of parts of the country that still can't get that, but like a lot of places can. You can buy that. Whether you want to is another story. This means that everything that we did 6 or 7 years ago has changed, right? First of all, measuring the link is harder. Well, how do you measure? Well, you got to fill the pipe. Well, the pipe is bigger. Okay, that means more data. Well, that means more disruption. That means if data is costly, in some places you pay for data. That's a consideration as well. This is, I think, one of the bigger challenges, which is what I said before. Earlier, when speeds were slower, you knew where the bottleneck was. It was your ISP. Now your ISP is getting pretty fast. Well, the bottleneck's in your wireless, or it's in your laptop, or it's in your set-top box, or it's Netflix. You don't know where it is. All you know is that number isn't basically anywhere close to what your ISP says it is. So these bottlenecks are basically moving elsewhere, right? So is it my home network? Is it my ISP? Is it Google, right? Everybody's basically trying to not be the bottleneck. So this is a really exciting time. It's also a really interesting time for figuring out how do we measure performance, where do we basically isolate the bottlenecks. We've done a little bit of work on this too. We've looked at the home wireless network. This was something basically we did in collaboration with the FCC as well. I'm going to talk about both of these in a little more detail in the next 2 slides. Both looking at the home wireless as bottleneck as well as interconnection, which is basically where 2 ISPs connect. Okay, so what this basically shows, we developed a tool. I'm not going to talk about how we did it, but basically by watching traffic going through that home router that we deployed, we can see whether or not the slowdown turns out to be on the home network side or on the upstream side. Okay, we called it home or access link. I think our original name for the tool was Where's the Fault? The FCC didn't really like that acronym. But basically what you can see in the size of the circle basically is the download throughput, the downstream throughput. So the bigger these circles are, the higher up and to the right you go, the higher up and to the left you go, meaning most of the time in those cases where, you've got a pretty good access link, you've got wireless problems, okay? This was a study we did in about almost 3 years ago now. Here's the statistic. This is obviously a moving target as well because home access points are getting a lot better, right? So everything's kind of getting faster at the same time. So that number is going to keep changing. But the point is basically, there's a constant race and seesaw between like where is the actual bottleneck. So we need to sort of keep developing these techniques to identify the bottlenecks. Another place where a bottleneck can show up is interconnection. We did a study on this. Actually, this was in developing regions. We did this one, a lot of the measurements we took were in South Africa. On the y-axis, we have latency in milliseconds, and on the x-axis, I've got cities sorted in distance from Johannesburg, South Africa. So if you can read those are basically kilometers. Okay, so if packets traveled like the speed of light around the Earth, you'd expect this plot to go up and to the right. It doesn't. In fact, you see this weird effect where the latency to between Johannesburg and Nairobi is like twice the latency as it is to like Amsterdam or London. Any guesses? Like what's causing that?
Peering or
Peering is the answer. Now, where are the packets going?
Oh, I was going to guess they go to a hub and then they go out.
Yeah, they go to a hub and out. In fact, the hub's like in London or Amsterdam, right? So the packets are basically going all the way up to Europe and then back, right? Okay, that's why they're twice, because they're basically going twice the distance. You've also got weird effects if you try to go from Africa over to, to Asia and Australia. Interesting problem. This is not purely a technical problem. This is a problem of like internet being a network of networks, right? If two networks don't connect, right, there's, they basically got to go through a third point. Sometimes that third point's really far away. In talking to people in some of the countries in Africa, like Uganda, about this particular problem, you realize there's political and social problems going on here as well. There can be nationalist tendencies and other things that say, no, we don't want any internet service providers that are from other countries like coming to our exchange point. Right? But this is a case where, again, it's not just how fast is my access link, right? There are other things going on in the network. Turns out, though, that even if we could basically make that access link faster, the web pages, you can basically crank up throughput as much as you want. Your web page isn't going to basically load in your browser any faster. This is again something we did on the FCC, in collaboration with the FCC, and beyond like a few tens of megabits per second, your web page basically doesn't load any faster. What's going on there? It's latency, right? It's the time you basically got to look up that name and get an internet address. You basically got to connect to the server. All these objects are relatively short for the most part. They're small. They're not huge objects, which means most of your transfer time is in setup. Right? So I can make that pipe as fast, I can make that road as wide as I want, right? It's not going to ever let me get to the loop in 30 seconds, right? Okay, so it turns out streaming video doesn't actually need more throughput either, right? So 4K videos, right? There's not a lot of 4K content on Netflix yet, but by all indications here, we're talking maybe many tens of megabits per second, 50, 70 at most. 1080p is like 10 to 20 megabits per second, depending on the video. And you can see that here, right? This is basically the capacity that we're measuring on the link for that user. Each dot is basically a user application combination. You can see basically that the max utilization for any of these applications is not maxing out the capacity. That brings me to basically the forward-looking part of this section of the talk, which is like, maybe we should be thinking about not just how do we measure speed as the way of characterizing performance and presenting that to users and how ISPs advertise to consumers, but actually, what about the quality of experience that users are actually having, right? How do the applications perform, not just how big is the link? Yes.
When you get that picture for the video streaming, is it similar for things like video conferencing where you can't spend as much time ahead of time figuring out like optimal compression, et cetera? Yeah, it's very different. We haven't studied video conferencing per se, but we have looked at, say, Netflix versus YouTube, and it's very, very different actually, because Netflix does everything in their power to avoid rebuffering, because you don't want your movie rebuffering, whereas
YouTube, basically, the metric is like start playing as fast as possible, which is called startup delay.
So then do you hit this capacity limit? I mean, I guess you said you didn't study it, but do you speculate that you hit it in these other settings?
Actually, I'm coming to that in the next part of the talk. Very good question. Yes, it matters for some metrics more than others. So I'll talk about startup time, and it matters a little bit for that one. But this is an open question in some sense. But let me flag that, and when I come to that, I'll mention it again. So really what we want to know is how the applications are performing. So this is sort of my, my current stump, if you will, is, look, we got to do something besides speed testing. We got to do something besides filling the pipe. Currently, the state of affairs is like, oh, if we want to measure video performance, we build a YouTube client, or we build something to emulate YouTube, and we figure out like how well that's performing. Well, now you got to do that for like Amazon, Facebook, Hulu, Twitch, Netflix, etc. Oh, and by the way, all those clients are changing all the time, and there's like 50 million different versions of each one. So, so there's a whole bunch of problems with application-specific tests, right? The speed test not actually, for the most part, with, reflecting the performance of the application. Startup delay being a possible exception. And also the paths are different, right? Like Netflix, YouTube, or they're running their own servers. You can measure that speedtest.net is going to some server somewhere. Usually they try to make it somewhere nearby, but it's not a Netflix server. So your speed to that server isn't going to tell you necessarily very much about the path to the services you care about. So what can we do instead? Well, users are, they're browsing a lot of video. Why don't we just measure it, right? And then try to infer basically what the heck is going on in the videos people are watching, and then maybe we can correlate it back to speed and see if, the question that Rebecca asked, like if there's any correlation there, like, hey, does this faster speed actually translate to anything meaningful, and at what point do you see that need? So we got this idea, like, let's just measure it. Let's, how hard could it be? Let's just basically watch, passively capture the video. We can measure bytes per second there, right? This is straightforward. And then we'll basically translate that to, things that users care about. And this basically came to our attention. Some folks at the Wall Street Journal who were still working with almost 2.5 years later, they came to us with this really simple question which relates to what you said, which is like, well, ISPs are telling users when they have problems with Netflix, like, well, just upgrade to a faster connection, it'll all get better, right? Well, is that true? We suspect that it's not. We don't have any data to like, back up that suspicion. So let's look at this. Like, does anything get better? Do most things stay the same, or what is it? So we basically started down the path of like, well, sure, how hard could it be? Let's basically just measure the rates that these videos are streaming, by passive capture, compare it to the speeds, and we're done. Well, turns out, if you know anything about video streaming, that it's a lot harder than that, because every one of these, as you mentioned, like some of them basically burst at the beginning, some of them basically try, sort of stream out segments in a more even pace. They're all different, right? And that doesn't come to anything about what's the resolution of the video, which again, if you know anything about video resolution, you know that the bit rates that you see depend a lot on the content as well. So, first things first, the system has some interesting components. I'm not going to spend a lot of time here, but I just want to point out that there's basically an interesting systems aspect to things we had to basically do to make the passive traffic analysis work. One is, how do you know you're watching, how do we know the user's watching Netflix? Well, that's actually fairly straightforward right now if you're willing to basically put a lot of elbow grease into it, because you look at the domain names that the client's looking up, and if you know what those names are, then you can say, there's been a lookup to Netflix, watch this particular connection. It's actually not quite that easy, because Netflix has a whole bunch of these names, and they're not netflix.com. They're like, some content delivery network name that's, a little bit gobbledygook, and they're changing. So there's a problem looking ahead, I think, that will be very interesting here, which is like, how do you basically make this session detection a lot more automatic? There's another problem coming too, which is that we rely on the ability to see those domain name lookups, and that ability may be going away in the next couple of years with the encryption of DNS traffic as well. So just the question of, is the user watching video, and what video service are they watching? Right now is a semi-solved problem, but in terms of automation, in terms of dealing with encryption, it's going to get harder. I'm going to basically talk about this aspect of our system, which is once you get the, the statistics, you basically want to infer those higher level features. Yes?
Are you like injecting yourself in the network so that traffic goes through you and you're reading it? Like, is that how you know?
Two ways. Like one is we have like an inline device where the router basically is set into bridge mode and we're right on path. Turns out when you get up above like 200 megabits per second, then it gets really hard to not like become the bottleneck yourself. So we have like going up to like the gig deployments that we have, we're now basically listening off of a mirror port on the router. Yeah. So basically, again, presenting something that like users want to see. This is an example of this system in action where users streaming Netflix there. Now basically they're streaming Facebook, and we're able to basically see, there's your YouTube session. There's your there's your Netflix session. There's your Facebook session. Here's a speed test. So we can see now, like, okay, this is what the user's doing. Now, this graph doesn't really tell you anything much except, hey, there's a Netflix session or there's a YouTube session and there's how much data is being transferred. That's a start. It's not really what we want to know, right? We actually want to know, like, how's the application doing, right? And that's where basically this machine learning and inference problems come in. All this traffic, it used to be easy, by the way, like before Netflix encrypted their stream, it was like easy because you just look at the HTTP request, the so-called dash request, you can see the resolution right there. Boom, you're done. Now the traffic's encrypted, you can't see any of this, which means we have to figure out based on this time series data, if you will, what are the metrics that actually affect users' quality of experience. This is not our work. This is from other work where people have looked at the same problem in the context of YouTube. But they've basically defined these as interesting quality of experience metrics. Startup delay. How long does it take to start playing? What's the resolution? That should be resolution changes, right? Like, does the resolution change during playback? Does it rebuffer? There's been some past work doing this, like just for YouTube. Using a whole bunch of things that basically required offline analysis. So our question was, can we do it for a whole bunch of different services? And can we do it using features that are lightweight enough to sort of enable the prediction? This is too small to read, that's intentional, because I don't want you to look at all the features, but this is basically just to demonstrate that we can do this with a bunch of features that are very, very lightweight, okay? Like counting the number of packets up and down, counting the segment size, counting the segment inter-arrival time, etc. We also have basically looked at, like, obviously if you train your model on the service and then test it on that model, you're going to do pretty well. This is precision recall, right? So you're doing obviously pretty well. Turns out that basically the model generalizes as well. I'm just showing one example. This is like inference of resolution, like am I at 720 or 1080, etc. Turns out that this basically works pretty well for the four that I mentioned. Here's the other thing I mentioned. I showed you quickly those features, right? This is basically ranked feature reports. So again, I'm not going to read them all to you, but here's the interesting idea, which is that a lot of these important features are direct or derivative statistics of things like how big are the segment sizes, right? How big are those segments coming down, and how are they spaced? These are things that could actually be measured in a fairly scalable way in a broad range of devices, ranging from like the home router to the CMTS and the cable, the cable system to the transit network. So looking ahead, what I'd like to basically do is do this in real time, build the system to basically implement that model so that we can do this kind of real-time inference both for the users, the ISPs, and the application service providers. And maybe get back to that question that the journal reporters asked us like almost 3 years ago, which is like, hey, how does speed actually relate to any of this? So that's something that we're still looking at. Let me talk about security.
Just before we move on to the next topic. So you're also interested in policy. So given the complexities in mapping from kind of low-level internet speeds to quality of user experience, what does that mean for things like net neutrality and if you can't even measure it properly?
Yeah, so one of the interesting things is, obviously, I think many people are probably aware that net neutrality is currently not a thing.
Yeah.
It's being litigated.
Right.
However, one of the aspects that has been preserved is this notion of transparency. So all this no blocking, has been wiped out, but even in the existing law, it says something about like, ISPs need to be transparent about the performance that they're delivering to consumers, and like, what does that even mean, right? Like, how can they be transparent if you don't even know what they should be reporting? So this all relates. And before the government shut down the Federal Trade Commission, this is now like in the wheelhouse of the Federal Trade Commission due to the way the laws have shaken out. They are basically due to have a hearing on advertising in this space and sort of what's truth in advertising. So yeah, this is going to become a pretty hot topic again.
So the flip side of all of this inference for, what application you're using, and I know people have done studies for inference on exactly what video you're watching, right, based on the fingerprints
Yes.
of the frames
Yeah.
and so on.
Yeah.
How does that play into privacy? Isn't that the other side of this?
Yes, there are definitely a lot of connections here to privacy. I think some of the work on sort of connecting, like, hey, I can see exactly what video you're watching, depend on having basically labeled data in a sort of closed model where you basically have access to the video library. It is possible. Let me sort of leave it at that, and I'll maybe return to it when I get to the third part of the talk. I haven't looked at it specifically in the context of video, except to say, like, we're trying not to look at that. It would be better.
The general question is, if you get a much more nuanced view of performance,
Yes.
isn't it inevitably privacy invasive?
It
That's
is.
the question,
Yeah,
right?
it definitely is. I think we can, let's talk about that one
Yeah,
towards the end,
okay.
because I think it's going to come up again. Yeah, very good point. Okay, let me talk a little bit about security and, sort of trustworthiness. Okay, so started off with financial scams, right? Scams, et cetera. This is basically a long line of work for me. I'm not going to talk about all of it. But the theme essentially is data-driven attack detection and prediction. These are all basically machine learning problems. Like, hey, how do I detect that, like, any piece of email is spam, or that actually an attack is about to happen, right? Or that a scam is about to be launched. And I'm going to talk about prediction. I'm actually going to talk a little bit about this last piece of work, which is like, how do you figure out that basically a scam is going to happen before the emails are even sent? Can you predict it? Well, the insight here is follow the infrastructure, right? So, of course, at some point there's, you get some junk in your inbox. It's like asking you to, give up all your bank details. But stuff happens before that, right? Someone's got to basically set up a website to do it, right? Or if they're selling you pills, right, they've got to set up the pill website. Even before setting up the websites, right, they've actually got to do things like register a domain name for their website, right? And we've looked at all of these, actually. I'm going to talk a little bit about this last step here, right? Because the insight is, if you can every one of these creates some exhaust, if you will. And if you can spot that, you can actually catch this stuff before it happens. Just a little background, right? You want to register a domain name. Feamster.com happens to be taken, but I could still get work for a bargain price, right? You've probably tried this, so you've seen this part of the process. What happens behind the scenes if you're sort of registering your domain name is that basically that gets registered with whoever manages the so-called DNSZone.com in the case of VeriSign. And they basically manage the registration database and push out basically some of these records to the authoritative. Okay, so insight or sort of hypothesis. Well, the way that scammers do this is probably different from the way you or I do it. Right? Let's look. Are there things that are different? Well, at first blush, yes, right? So turns out that basically spammers have their favorite registrars that they use. That alone doesn't really help us because we like those too. Those are our favorites. But there are other things that they do that we do less of, like register 500 domains at once. There are actually tools that you can use to register 500 domains at once on the cheap, right? We tend to not want to do that. Spammers like to do that. So basically, we worked with VeriSign on this. We saw basically domain registrations every 5 minutes. And you can see that basically when a spammer comes in, there's a lot more activity. We modeled this, right? Turns out you can model this as like a compound Poisson process. The intuition behind that is basically each one of these customers is arriving independently at some fixed rate. But each of these customers is basically making registrations drawn from some distribution. So you can basically model this. Okay, so that's one thing we looked at is basically how does this fit into a compound Poisson model? Does it or not? Basically can give us some clues. The other thing we looked at is basically where this stuff falls in the domain registration lifecycle. Okay, Okay, so you register a domain, right, it's active, at some point it expires, you probably, if you have a domain, you've probably seen that your domain is expiring soon, please renew it. Well, if you let it expire, there's a period of time basically where, there's a grace period and then there's a delete, and eventually basically it's released for someone else to get it. So when something shows up in the database, we can basically, the registration database, we can say like, has it ever been registered before? If it's been re-registered, was it like expired and immediately re-registered, or was it like dormant for some time and re-registered? It turns out that's a really useful feature because spammers love domains that are old, that have been, because they've already got some reputation associated with them, typically good. So one thing that we observe is that these spammers commonly re-register these expired domains, especially when they're doing it in bulk. Okay, so I'm going to skip the stats on that. But basically, we can look at those lifecycle features. We can look at basically, are these things showing up in batches? We can also look at like, where are these domain names being hosted at? Where are they being resolved from? And if we sort of combine all three of those, we basically can build a model that predicts, this domain was registered, it's basically gonna be used for an online pharmacy or an attack of some kind before a spam message ever even gets sent. For this particular model, we use something called a Convex Polytope machine. It's kind of like an SVM, it's sort of like a piecewise SVM. We use that for a variety of different reasons, one of which was that one of our co-authors invented it, but it has some other nice properties as well. Okay, so what do we do? Basically, we trained this on data from .com. Right? We had basically ground truth of these domains showing up in blacklists, spam traps, and other places. And we basically tried to say, could we catch this stuff before it showed up in our ground truth data? Because all the ground truth data had timestamps on it. So we could do that, and we could basically do that at a pretty good rate of accuracy. Let me spend just a minute or two talking about where this is, that was one kind of unwanted traffic, email spam and scams. The next sort of thing, if you will, is disinformation. Information scams, if you will, fake news. I said I wouldn't use that word. But it so happens, and this was basically an insight that I had actually talking with a collaborator, Jonathan Mayer, who spent some time on the Intelligence Committee in the Senate. I was talking about this problem, and I said, hey, we did all this work on spam, and he said, actually, I've met with a lot of these fake news people, and it turns out they do the exact same thing. Let's try it, right? So we could do the same thing. We can look at all the registration data. In this case, we're looking at the certificate, properties of the certificates. We're also looking at basically, where is it hosted? Other properties of the web page, right? Is it hosted on WordPress? Are there same Google Analytics IDs across many of these apparently independent news sites? Bunch of other different features of that nature. It is working fairly well. This is work in progress, okay? So literally this week we got this system set up basically where we're listening to the Twitter fire hose. We're taking every tweet from the fire hose is 10% of all tweets that have the word news in them and a URL. And we're saying is it news, right, or not? If it's a news site, is it legitimate or does it look fishy, okay? And every day now we're catching a few of these. This is from 2 days ago. The National Times apparently has some interesting stuff about Michael Jackson and Ghost and other things. Anyway, these are, the rate at which these are coming is basically tens per day. Okay, so it's obviously gonna, we're gonna basically need to find ways to ferret this stuff out. And we're looking at this now mainly from the machine learning and detection side of things. This obviously has connections to users and how you basically present this in ways that users can make sense of it. And that's some of the next steps of what we're thinking about. Okay, finally, third challenge, privacy. We'll start off with, I'm going to focus on the smart home. Mostly, I guess we can talk a little bit about video, but you'll see some of the stuff here actually relates directly to your earlier question. Let me first start talking about attacks and weaknesses, and then we can sort of end with defenses. Unfortunately, I'm going to warn you that I have no great answers on defenses yet, but this is, again, sort of ongoing. This, again, was another one of these questions that I just loved because it was yeah, this would be interesting. How hard could it be? Let's just get a bunch of devices, connect them, through some passive monitor gateway, we know how to do passive traffic monitoring. Now let's, and this is actually how we got into this, right? It was like, hey, we've already got stuff in homes. We already can capture traffic. Let's look at some other interesting stuff. People are connecting lots of interesting things. Then we were like, it would be interesting to see what kind of like data these devices are sending and like to where. And we started thinking like, oh boy, how are we gonna like man in the middle these encrypted, connections from these devices? Because we really want to see like what data they're sending. Yeah, and then it turns out like it's not that hard. Like if you just look, some of this stuff is in the clear, right? So Nest actually is one of the better behaved ones we looked at. But some of the weather updates were basically coming right over in the clear. So you could figure out just by watching, like, basically where these devices were. They fixed this, after they, some people took note, including the Federal Trade Commission. So this is my student presenting at the Federal Trade Commission on this particular issue. Okay, so just encrypt it, all the problems go away, right? This comes straight to your question. Well, not quite, but in the IoT sense. Well, that doesn't quite help.
I'm sorry, is that illegal activity, or they were just shamed at the?
Not illegal.
It's not illegal?
Yeah, no. Yeah, we had a side question about protection and enforcement. Yeah, not illegal. Encryption alone doesn't help, right? Like, okay, just encrypt that stuff that we just saw in the clear. Well, that doesn't quite help yet. So one thing is like DNS, the domain name system, right? That traffic is all still completely in the clear. Okay, so you can look at that stuff and basically provides pretty good fingerprints on devices. Okay, once you figure out what device it is, right? So I can figure out that you've got a sleep monitor in your house because there's basically names like Sense, which is the name of a sleep monitor. I can figure out that you've basically got a Nest security camera because it says dropcam.com. Okay? And once I figure out what those devices are, because it turns out those sets of domains are pretty unique to the device, it's pretty darn easy if I know you've got an Echo, right, to figure out when you're talking to your Echo just looking at the volume. It's not just about privacy and activity recognition, that's one concern, but another is actually control. Okay, so here's an example where you're in your house, picture this, you're browsing the web, you visit a malicious site, right? Suppose there's malicious JavaScript on that site. Well, it so happens that that JavaScript can perform something called a DNS rebinding attack. What that basically does is like your browser does a lookup to a domain, and that JavaScript will return your browser an IP address that's internal to your house. Well, your TV actually has it as a web browser on it, as it turns out, and you can do things like send queries and HTTP posts and requests to your TV from the browser if you succeed in launching this kind of attack. So this is a place where all bets are off as far as security. What do we do about any of this? Well, first thing, we can study and expose the behavior. I've been talking about that. We can obfuscate the traffic, right? So we've been talking about, we've done some work on padding the traffic in ways, not in the video case, that's an obvious thing that one could try, but in the IoT, the smart home device recognition category, we've tried, we've been working on padding defenses. Another is you could try to redesign some of the protocols, and as time permits, I'll talk a little bit about what we're doing there. Another thing you could do is try to work on better architectures for the home network to isolate these devices better, and that's, again, very early stages in our thinking about how exactly to do that. And that turns out it's tricky because like a lot of the value here is these devices talk to one another, interact, and that's cool. Like, hey, I can like turn the movie on and the lights dim, that's neat, but it comes like exactly that kind of lack of isolation and interaction is exactly the kind of thing that allows that like, hey, web browser, malicious script to control the TV. What are we doing in this space? Well, one thing, we got a bunch of undergrads in the room. We got them started playing with devices and thinking about defenses. They started by building a dashboard. There's a bunch of different undergrad projects that basically happened here, everything from like detecting insecure default passwords to detecting clear text transmission. Here are three of the undergrads presenting to on Capitol Hill. That's Rush Holt, president of the AAAS. And here are a couple of the undergrad projects that they did, detecting clear text in medical devices, and looking at basically, hey, when is my camera that I plugged in like participating in a large-scale worldwide denial of service attack? We were inspired by these sort of undergrad projects, and postdoc now is basically working on a tool that that basically does this in a much flashier and more complete way. And all credit to him for developing this. This is fantastic. But as you sort of started with this question, like, if you're familiar with this tool called Netalyzer, if you're not, basically you can go to a web page, click on a button, and it'll tell you everything about your network. Like, hey, how fast is it? Where are the buffers? Like, or do you have IPv6? Could we do the same thing for IoT? Right? Could I run something from my laptop in my house and basically just have it tell me about everything that's connected to the network? Turns out, after a lot of sort of false starts, the answer is yes. I won't get into the technical details of how it works, but for those of you who are familiar with networking, it's based on ARP spoofing. Okay, we basically become the hub for as long as time as this application is running. We don't take over the network forever, just for a period of time that you're interested in looking. Basically, sort of identifies the device on the network and tells the user who this is talking to. So this is the smart fridge. You'd be interested to know that that smart fridge I showed you before talks to obviously Samsung, but also Google Ad Services, Nielsen, Core Metrics, DoubleClick, pretty much you name it. Okay, here it is in text. I'll show you like a quick video. So you can basically click on any of these devices. This is my house. I was pretty shocked to see some of these things. After this, I've unplugged everything. Okay, so last sort of note on defenses, right? I've talked repeatedly on the talk about the domain name system. Turns out, basically, this system we use to map names to addresses, it's really cool. Like that Clark paper from the 80s talks about how great, all these protocols are, except we sort of forgot about the whole security and privacy thing, okay? And you've probably sort of seen some of this in the press, like, oh, your ISP is giving away your browsing history to the lowest bidder. Well, what does that all mean? Well, all that stuff is based on the insecurity of the domain name system. Okay, so when you do a domain name lookup, you basically do it to something called a local recursive resolver. That's, if we're sitting here in this room, there's probably a machine in the University of Chicago that's doing it for you. Google has one. Okay, I'm going to come to that, right? But your ISP has one. And like all of this is clear text, right? So all the sort of hype and hoopla in the news is about like, oh, your big bad ISP is basically going to see all this stuff. They're going to use those DNS names to figure out that you've got a sleep camera, and they're going to sell it to your insurance company. This is all bad. Okay, it is bad. Okay. Okay, I think I can skip the background on DNS because I've given it to you. But so here's basically what we started hearing about a year ago. This was released on Quad 1, aka April 1st, not an April Fool's joke. Cloudflare was like, no, don't trust your ISP. Like, we've got this awesome DNS resolver. Trust us instead. We won't do anything bad with your DNS data. Why do they want it? Well, they run a content delivery network. That's a completely separate talk. Okay, so they've got other reasons to want to see your DNS. A lot of people basically stepping in and saying like, hey, just make us this box, right? And everything's going to be fine because it's no longer Comcast, it's Google. Okay, what could possibly go wrong? Right, give all my DNS queries to an advertiser. Nothing's wrong with that, right? Okay, well, we came to the, by asking the question, what if we could just basically make it such that the operator of this box couldn't identify both the query and the IP address that sent the query? Okay. So here's the gist, and I'm going to skip over some of the crypto details here. But the main idea is you want to obfuscate that DNS query before sending it to the local recursive resolver, right? So you're basically going to, in fact, I will show you just briefly how that works. But that first hop is going to obfuscate that query, tack on something else to the name that basically causes that whole blob to be sent to a third place that can unwrap the package but never saw the IP address. Okay, so I'll show that to you basically in graphics. Okay, so the old picture, now we basically insert a new resolver. It's an authoritative. What happens here? Well, we start off with a domain name. Okay, that gets basically encrypted with a key that is known to this machine over here. Okay, how do we get this blob over there? We tack on something to the domain name that's in the clear. Right, that causes this box here to create a referral. Okay, that blob gets referred right to the operator of this oblivious DNS. This guy has the key, right, and can basically peel that off, right, and do DNS as usual. And then the process basically, repeats in reverse.
Didn't you also defeat the cache that's in the resolver?
Great question. That's like the biggest problem with this particular system is you can no longer do caching here. You can do caching here, but there's some implications there. Yeah, that's right on the money there. That's the biggest question with this particular system is what are the implications for cache addiction. There's another thing, and in light of time, I won't show you all the performance graphs, but one question with this system is what about caching? The other is what about performance? It turns out that actually performance is pretty good because the crypto operations here are pretty fast. And the additional latency here is the latency between this box and this box. Okay, so now there's actually a very interesting trade-off because for performance reasons, you want these to be close. Okay, but for privacy reasons, you don't want them to be the same party. And I don't know if they're in the same building, maybe that's also a concern. Okay, so interesting trade-offs there. There are a bunch of other practical considerations, which I'll show you, but I won't describe in detail. There's something called EDNS zero client subnet, where basically an IP address gets attached to the initial query and passed on. It helps content delivery networks map the client so that they can send them to a nearby web cache. We don't like that. Some resolvers strip it, some don't. And then there are a whole bunch of challenges dealing with the way that the DNS protocol is actually implemented versus how it's specified in the protocol. This is why we build things. We're like, sure, we'll just shove it in the optional record. It turns out most implementations don't support the thing that the standard describes. So we're like, oh, boy, we got to shove it in the name. So there are a whole bunch of interesting challenges there. Okay, finally, I just want to wrap with a couple comments on, just wrapping up everything I talked about from usability to trustworthiness and security to privacy. I've talked a lot about technical interventions, but as Mike mentioned, it's not always just about technology. And another one of my interests is basically taking the data and the insights that we've gathered from each of these projects to better inform the policy discussions in two different ways. One is basically helping articulate the state of affairs, right? So here's basically a recent hearing at the New Jersey State Assembly where they're talking about the net neutrality laws, and they said, please tell us about when is, net neutrality basically says don't prioritize all bits are equal, right? Well, turns out to manage a network, sometimes you need to make some bits more equal than others, right? Video conferences, it's more important that the packets get there than, say, your Dropbox backup, right? So please explain the differences here. So that's one way that I help engage, is basically explaining basically the way things work. The other is basically helping the policymakers understand the boundaries of the capabilities of these technologies, what they can and cannot do. Because a lot of times it's like, well, okay, you guys just go off and work harder, be better nerds, and this problem will go away. The law enforcement will get access to phones and it's all fixed, right? Well, turns out that a lot of the things that are being asked for on the wish list are not even technically possible. Or sometimes it'd be like, well, it'd be nice if that were possible, and now we have a computer science research problem to work on. Okay, so those are what I see as the three challenges for the next era of the internet. Make it usable, make it trustworthy, and make it private. And there are technical challenges there as well as policy ones, which I look forward to continuing to work on. Thank you for your time, and look forward to any other questions.
So how do you see things changing once we move into larger broadband networks like 5G, especially since that seems to be the mode of getting people online in developed countries, especially with usability concerns? Because gateway now shifts from the home to a cell tower and trying to do these performance metrics for the usability tests. The dynamics going to change. So how do you anticipate being able to do measurements?
Yeah, there are a whole bunch of different questions wrapped up in there. I mean, basically, you're talking about 5G, which means basically faster speeds, also faster speeds over wireless. interesting questions there. I think, again, sort of the sort of bottleneck shifting is going to be a question. Other things related to wireless, I think like a lot of interesting questions there relate to spectrum use and management. What's going on in unlicensed spectrum, which is not strict. I mean, 5G is really about licensed spectrum mostly, but there's also stuff going on in unlicensed spectrum, and I think there's going to be some interesting things related to measurement. Like, okay, there's something called LTE in the unlicensed spectrum, right? Well, how are you going to make a phone call when there are like 100 light bulbs in the room, like all competing in the ISM band? So I think there's some interesting questions at the intersection of spectrum management and performance, particularly in the unlicensed spectrum, but I think also in the 5G space on a lot of the interesting questions are in spectrum management. I think actually probably there's some people here, like Professor Zhang and others who work in wireless who probably know even more about the challenges as far as performance go.
So a lot of the theme of this talk was measurement, right? And have you thought about how some of these ideas would work intra-data center or intra-cloud, public cloud, private cloud? Have you guys thought about not just the broader internet, but something that's kind of more restricted where we know a lot of application semantics?
I'm glad you asked. So inter-data center is not something I've looked at because basically I don't run data centers, and I prefer to like measure parts of the network that like I can see. You can obviously work with Google and Facebook if you want to work on those types of problems. However, one of the interesting developments in the internet that I didn't talk about, but I think is the other sort of big sea change, is that it's flattening. Right? It used to be that if you wanted to like measure, performance of an end-to-end path, you had to be like crossing 4 or 5 different networks, and now like the vast majority of traffic is going like 2 hops over interconnect. It's like Netflix to Comcast, which means like, okay, there's this network, there's this big network, there's this big network, and there's an interconnect. This means basically that we've reduced this to a problem that we can measure end-to-end, right? Because I know how to measure the access network. I actually know how to measure the interconnect as well. There are other people who know how to measure like the data centers and the server side of thing. And I think there's actually hope now where we talk about like, let's measure the whole internet for all paths. That used to be like an intractable problem because that like first picture I showed, you can't make sense of that. But you can absolutely make sense of like Netflix to Comcast. That's a very tractable problem.
Well, so another view of that would be the internet's disappearing inside these black spaces, right, which are inside of Google's network and so on. Which ties to all these questions. So one question would be, will it make sense in 10 years to define internet research as excluding that stuff? Or, does it it's like dark pools in financial, markets, right?
Mm-hmm.
I mean,
is that the internet?
Is that effectively the internet is the question, That's a philosophical question.
I know, yeah.
That's right.
That's
since you think about policy, right?
No, that's an interesting question. I think we're going to have to think of it as part of the internet, whether we want to or not, because that consolidation is inevitable. I mean, it's more than inevitable. It's like already happening. What that means for okay, so actually twofold. One technical, one policy. On the plus side, right, maybe it means we can measure it or we can deploy cool new protocols. I mean, Google's done a lot of work like deploying Quick and other sort of fancy transport because they control the whole thing, right? This is where like a lot of software-defined networking and other innovation, like why are most computer networking nerds so interested in data centers is because you can control the whole thing. Well, if the internet becomes, what you call it, sort of a box, well, that's appealing in a sense because we no longer have to talk about future internet. We can just basically do stuff, in a box. I think the flip side of that is actually interesting though, and sort of has bearing on policy, which is this consolidation question. Okay, used to be that like if there was a government request for data, they would have to get a search warrant and like knock on your door and like take the hard drive that's sitting under your desk. That's no longer the case. They just basically have to, go to Google and they go through secret courts and basically get stuff without you ever knowing it happened. Also, content delivery network like Cloudflare can decide like, hey, we don't really want this content hosted on our site. Let's just basically take it down. Some of that stuff we don't want to look at either, but the very fact that they can make that decision is something to think about. And I think at the very beginning of the talk, is this is just going to be about packets, you're going to move up the stack. I think another up the stack question, again, is like access to information, like everything from search portals to news to social media, right? Driven by algorithms that are dictated by personalization and preferences, et cetera. What you see isn't the same thing as what I see, and it's also like we don't have very much say in what that is. And it's controlled by a very small number of parties. So I think there are a bunch of interesting questions that are both technical and policy related.
Hi, thank you, Nick. So my question is regarding the smart home. So, so far, I think you seem to conclude that a lot of the trouble comes from the device manufacturer trying to take the shortcuts, making the device cheap and nice, right?
I may have implied that here.
So, if our research basically allow them to change that behavior so that the smart home device will behave the normal device, do you think that will solve the problem, or you think there's deeper problem beyond that regarding the smart home or IoT?
Some of it, yes. I think basically there's like very good work to be done in that area as well. It's not my area, but I know others are working, like people who work on operating systems and other things are looking a lot at like process isolation, other things basically, so that like if I install a shared library or an app or something on this device, that it doesn't basically get access to everything. So there are interesting systems problems there that others are working on that I know less about. I think even if we know how to solve them technically, it doesn't mean that like economically they're going to be solved, because all Google devices or all Samsung devices may behave properly, but that doesn't prevent you from buying the internet connected photo frame on Amazon because you like the color, and who knows what that's running. So I think we can probably solve this at the device level for like a good chunk of the market, but there's always going to be the Dahua security camera that launches a denial of service attack on Dine or what have you. And then I think the other side of that is that part of the story is security, and then the other part of it is privacy. And in some cases, the incentives point all in the wrong directions on privacy.
Okay, one more.
Hey, Nick. Cool stuff. So I was really interested in the stuff that you talked about at the network infrastructure level, looking at misinformation. Given that this is a much more adversarial sort of context, have you guys seen any cool effects, or sorry, not cool, but interesting effects where the potential misbehavior is adversarial, so they try to obfuscate their behavior at the DNS or lower level?
Haven't seen it yet, but I think it's probably coming.
Yeah. I mean, I'm fascinated to sort of find out what's coming.
Yeah, one thing that we haven't tracked, but I think would be a really interesting thing to look at is if you remember the sort of UC San Diego work where they sort of like track the spammers to the, hey, there are only like 3 banks that are basically. So I think one thing that we are seeing is like a lot of common Google Analytics IDs, right? So a natural step here is basically to be like, who's behind, is those three sites that just popped up today, like are they at all related to the 3 that showed up yesterday? I suspect yes, but yeah, good stuff.
Great. All right, well, let's thank Nick for a great talk.